Hi students, it's Dr. Marks and our topic is data visualization constructs. So we're actually going to look at some data visualization examples. Now, if you remember, in the last lecture, we looked at tips for good data visualization. And we focused on things like readability. Can we tell what's going on? Is there too much going on? Is it too busy? We looked at accuracy. Is there something deceptive going on that maybe skews our interpretation? We looked at things like citing. If I'm using something from another source, I have to make sure that I'm not technically plagiarizing. It would probably never be our intent, but technically we're plagiarizing if we're not citing. And we talked about incorporating into text, not orphaning our graphics. So if we have a graphic, we need to say, as you see in figure 1, we need to point it out to the reader, and then we need to make sure that we tell the reader the takeaways. You don't want the reader to just show up at some point in a report and say, oh, there's a graph here, let me figure out what you're trying to do with it. So now what we want to do is look at creating some additional graphical constructs. And as we're doing this, keep in mind that we're still in that describing portion of the definition of statistics, and we haven't seen that definition for a little while, but we're in that middle part of the definition, still talking about describing. Let's start with thinking about how we might illustrate qualitative data. Now, we understand qualitative data versus quantitative data. We've seen this before. So we want to ask ourselves, how can we represent qualitative data visually? Because hopefully you agree, we can't use a line graph, right? We can't use a scatter plot because those are things that are plotting X versus Y, right? And so that's not going to work with qualitative data. We have to rely on something where we can represent qualitative groupings. So what might be some qualitative groupings of interest? Well, maybe we're looking at groups for different religions, or it could be months, right? Some kind of time element, months, years. Those are qualitative groupings. Gender, another qualitative grouping. So you're familiar with some things like pie charts and bar charts, which give us very easy ways, depending on how simple the information is that we want to present. So let's start with the simplest thing. We've got our pie chart, and I know all of you understand this. In this example, we see that we have groupings by quarter. So is it quarter 1? Is it quarter 2? Is it quarter 3? And so on. And so we do have little buckets. It's not quantitative when we say quarter 1, quarter 2, right? That is qualitative. So first thing we want to appreciate is we've got these colors, we've got a key at the bottom, right? But I also want to remind you, as we're creating data visualization constructs, we need to be clear in the title what exactly is being graphed. So if you look on the left graph, this is simply houses sold per quarter. So did we sell, 50 in this quarter? Did we sell 60 in this quarter? But if you look at the graph on the bottom right, now we're graphing quarterly sales as a percent of total. That's not the same thing, just simple number of houses sold versus quarterly sales as a percent of total. So quarter 1, what percentage of the entire time period does that represent? So you want to make sure that you are very clear in your identification through your title. But the other thing I want to point out here is that these legends are a little hard to read, right? You've got two blue colors that are pretty close together. And so please, when you're creating constructs, make sure the colors are different enough. Now, this might be something that's automated through Excel, but if it is, you want to override it and pick other colors. Now, I know you already know that if we have a pie, it has to add to 100, right? Or it has to be really close. If there's a little bit of rounding error, then you might see something that doesn't quite add up to 100, or it might be slightly over 100 simply because of rounding. That's okay. Now, here's our bar graph. And note that we have 3 different dimensions in this example. We have first groupings by year, right? 2006, 2007, 2008. And we have groupings by book type. If you look on the far right, you see that there's a legend. We've got blue for young adult, yellow for classics, red for mystery, green for romance, and then the brown color for sci-fi and fantasy. And those colors are very distinct from each other. But then we also have a dimension, which is the gross earnings, and which is our y-axis. Let's move on to talk about scatter plots. Now, we've already discussed scatter plots. We've seen them before in previous lectures. You might remember we talked about them when we looked at correlation, for example. So let's remind ourselves, in case you don't recall, what is a scatter plot? Well, it's simply an XY plot of the data. So we're plotting two variables, one against the other. Now, maybe my data set has more than two variables, but the scatter plot allows me to look at just two of them at a time. And so the goal is to see the relationship between these two variables. So my question for you here is, will this work with qualitative data? And I know we just answered this question, but think about this for a second. Can I use qualitative data with a scatter plot? So can I look at the correlation between gender and hair color and see if I have a visual pattern through a scatter plot? Well, obviously the answer's no. I can't do this with gender. I can't do this with hair color because, again, how do I put gender or color on an XY graph, right? XY graphs are measuring something quantitative. So clearly scatter plots are used with quantitative data. For example, we've got compensation of account representatives by experience. So I'm telling you, again, titles are important. Compensation of account representatives by experience. So that's telling you, I'm trying to show you the relationship between salary and experience. And of course, in this example right here, we see a pretty strong positive correlation. So a scatter plot can be very useful for this. But remember, a scatter plot can also help us look for outliers. And we agree that in this example right here, there's no big outliers. I see that pretty much all of these observations fit to a line. If I were to draw a line that was trying to fit these different observations, nothing's way out of whack, right? However, what if instead we have this situation? Clearly we have a really big outlier that we've got somebody with only what looks like 12 years of experience who's making a really large annual salary. So maybe somehow we added in some kind of big regional supervisor for account representatives. I don't know. But clearly we've got some kind of outlier, and that's going to impact our analysis. When we go to do data analysis, that's going to change our results. So we have to think a little bit about this. Let's move on to the idea of a stem plot. And this is something you may have seen before. Maybe it was called stem and leaf plot. But we're going to do a stem and leaf plot. And it's also a pretty simple way of presenting data, but it can be very handy. Now, the leaves of our stem plot contain the smallest digit in the data. The smallest digit is the leaf, and the stem contains all of the other digits. So basically, I'm dividing out my numbers. I'm taking the smallest digit, my leaf, and separating that from my stem, all the other digits. And from this, I have a distribution that's created. So you're probably thinking, what in the world are you talking about, Dr. Marks? Makes no sense. So let me just jump to an example. Here's a stem leaf plot. So a stem and leaf plot, a stem plot. Let's say that these are ages of people living in an apartment building. So clearly it's not a huge apartment building, right? Because I don't have a huge number of observations. So my leaf, notice, is my ones digit, right? We said that our leaf is going to be just the last digit. And the tens digit, that's going to be the stem. So from this, it's easy for us to illustrate a distribution. But I'm sure you're thinking, okay, what if my data set's really huge? Yeah, if you have a huge data set, this is probably not so tractable. So I agree with you that this is going to have some limited applications. And if we're dealing with huge amounts of data, this could be really cumbersome and too clunky. Now, just so you know, there's some notation that goes with the stem plot. So you see that 5 bar 2, well, that's separating the stem from the leaf. So stem of 5, leaf of 2, we have somebody in our apartment building who is 52. And if I have 6 bar 6, then we have somebody who is 66. So that symbol, I didn't even know what it was called. I had to look it up. And so I've learned that it's called a vertical slash, it's called a pipe, it's called a stick, it's called a bar. I'm probably going to call it a bar. So what if I have a person who's 101 and they move into our apartment complex? Well, remember, our leaf is that ones digit. So we have a 1 for the leaf. What's our stem going to be? Well, our stem here is 10. So from this stem plot, we can see that our ages are 1, 1, 2, 2, 3, 4, 4, 4, 4, 5, 8. You get the idea. On down. So if I give you a stem plot, you should be able to answer some basic questions about what are the ages of the people living in our building, if this was my example. But something else that you can do is that you can find the median. A stem plot's going to allow you to really easily find that median, which I have just indicated for you. So what's the median age here? 28. Now, do stem plots help us visualize qualitative data? What's the answer to that? Well, clearly the answer is no. So when we talked about scatter plots, when we talk about stem plots, we're talking purely about quantitative data. Let's move on to frequency histograms. A frequency histogram is a graphical version of a frequency distribution. So all we're doing is taking a frequency distribution and making it a graphic visualization. Now, the widths of the rectangles that are in a frequency distribution are used to indicate various groupings, and those groupings are called bins. So the width is going to be our groupings, bins. But the height of the rectangles are going to measure frequency. So when I put it together, I'm going to know which data fell into the associated groupings, also called bins. So what we're really doing here, gang, is that we're showing the data in intervals. Now, what would those intervals be? Well, it depends. In the above example that we were looking at with the stem plot, right, we have these natural groupings of 10, right? Because we pulled off anybody who has a 0 in the tens place, a 1 in the tens place, a 2 in the tens place, a 3 in the tens place, and so on. So we could potentially create a frequency histogram that looks like this. I want to point out that in the frequency histogram, we see no gaps between the bars. So this is different than some other graphical constructs. But could there be an absent bar? Sure. What if I have nobody between the ages of 10 and 20? If nobody's between the ages of 10 and 20, then that bar would be absent. So, no one in their 20s? Well, that green bar would be absent, right? We need to make sure that the size of the groupings, again called bins, are not too large or too small. In this example, with groupings based on an interval of 10 years, well, it's very readable, right? So it's important when we think about our groupings or our bins and how wide or narrow they are, we need to make sure that we can see the pattern. That's going to be important. So let's think about these examples. And these are examples of where we really haven't optimally designed the histograms because of the size of the bins. The bottom line, size of these bins matter. So look at the graph on the left. And what's going on here is that the bins are just too small, that it makes it hard to read. But on the right, the bins are too large. I don't really refine the data very well. I mean, I haven't offered the reader a whole lot of information here. I mean, I'm telling him how many people fall in a 30-year interval. So again, not too small, not too large. You get the idea. Now, how is this different from a bar graph? Well, we understand that this looks kind of like a bar graph, right? But frequency histograms are used with continuous data, right? We've got age, and it's a continuous variable. But first, we had to create the bins. So we created bins with a range of 10 years, but we are graphing something that is indeed continuous. However, a bar chart's different. A bar chart can be used for qualitative data, right? So think about what we just covered a few minutes ago in this lecture. Bar charts can look at some qualitative groupings too, right? We can look at number of people that are, female, number of people that are male. All right, so if I wanted to look at number of females, number of males, that bar chart would be an appropriate thing for me to use. So this might help us really see the difference between a bar graph and a histogram. So the bar graph on the left is for categorical groupings. And this, as we've already said, is qualitative. So look at the bar graph on the left, and we've got number of people who speak Spanish, number of people who speak Chinese, number of people who speak Hindi, French, English. You get the idea. But this is not a continuous variable, right? Because it's not quantitative. So our bar graph allows us to graph things that are qualitative. But on the right, we see that we're using only quantitative data. We have bins that are specified, but those bins in this example for year are 5 years wide, where year is a continuous variable. So that we can summarize this a little bit, if we're comparing the histogram to the bar graph, again, I'm just going to go through this quickly, but when it comes to meaning, a histogram refers to a graphical presentation that displays data by way of bars to show the frequency of numerical data. Again, it's telling you, hey, we're working with quantitative data. Whereas on the right, bar graph is a pictorial representation of data that uses bars to compare different categories of data. So qualitative. All right. It indicates on the histogram a distribution of non-discrete variables. In other words, continuous variables. Whereas the bar graph on the right, comparison of discrete variables, right? Things that are in categories. As we've already said, a histogram, we're looking at quantitative data, whereas with a bar graph, we're looking at categorical data. How about spacing? Well, the histogram, the bars are touching each other. There's no space between bars, except for there could be a missing bin, right? If nobody's in that bin, but the bin is still there. But with a bar graph, the bars do not touch each other. There are spaces between the bars. With respect to the elements, with the histogram, the elements are grouped together so that they're considered as ranges. But with the bar graph, elements are taken as individual entities. Now, this is a great question. With a histogram, can the bars be reordered? The answer is no, I can't reorder the bars because the bars are qualitative data that's continuous, right? Could I put 50 to 60-year-olds and then 0 to 10-year-olds and then 40 to 50-year-olds? That makes no sense. But on the right, if I have a bar graph, can I reorder the bars? Sure I can. It doesn't matter which one comes first, female or male. Width of the bars don't necessarily need to be the same with the histogram, but they do with the bar graph. So again, it just helps you understand that if you're looking at a graph, is it a bar graph or is it a histogram? So let's move on to something else that's interesting, and that's the box plot. The box plot is a way of presenting data based on a 5-number summary. A box plot is going to give us the minimum. It's going to give us the first quartile, and remember the first quartile is the 25th percentile. It's going to give us the median. Remember that median is the 50th percentile. It's going to give us the third quartile, which is the 75th percentile. And then it's going to give us the maximum. So a box plot is a way of presenting 5 things in kind of one neat, tidy package. So our graph is going to be comprised of what we call a box, hence the name box plot, and whiskers. So box and whiskers. And these things are going to indicate the 5 elements that we've just said. Minimum, first quartile, median, third quartile, maximum. All right, you get the idea. So this is a box plot. Not hard to understand when we figure out what all these elements are. All right, so we know that we are representing the 25th and the 75th percentile. But think about from a previous lecture. What do we get when we look at this distance between the 25th and 75th percentile? What did we call that? Q3 minus Q1. We called it the interquartile range, right? So the box plot, the box of the box plot, gives us the interquartile range. Now remember, that median is the 50th percentile. So if I say median, you need to be thinking, oh, okay, that's the 50th percentile. Now, one cool thing about the box plot is that it gives us an idea of the dispersion or spread of the data because it goes from the min to the max. But here's the deal. The box plot that I'm showing you right now is assuming no outliers. And I'm going to come back to that in just a minute. If we have outliers, it's going to look slightly different. So assuming that we have no outliers, our box plot, the whiskers, go from the min to the max. Box plots help us understand something about skewness of our data. So if it's normally distributed, like in this example right here, so if I have a normally distributed data set, right, it's symmetric around the mean, right, then I'm not going to have any skewness. We're not going to have anything skewed to the left or to the right. So look at this box plot, right, and we see that we have symmetry, right? We have symmetry in our interquartile range, right, relative to our middle point, and we have symmetry in the length of our whiskers. So we're simply symmetric here around the median. But we see the same area on both sides of the median. And as I just said, we see the same length of the whiskers. So everyone understands that this is clearly symmetric, right? If I folded it in half, it would fold right on top of each other. So when I have something normally distributed, when it looks like this, when the whiskers are the same, when that interquartile range can be folded equally in half, okay, then I have something that's normally distributed, not skewed. But we might have some skewness. So I've given you 2 examples of box plots where we see some degree of skewness. Now, if you look on the left, you see on the first box plot something with a positive skew. So by positive skew, we're talking about skewed to the right. Now look at the graph, the red graph of the distribution, and you see the positive skew. It's like we've taken the right tail and stretched it out. So it's skewed towards the positive, right? It's skewed right. But on the bottom box plot, we see a negative skew. And that's as if I've taken that distribution on the right, the red one that says negative skew, and I've pulled it towards the left, towards the negative numbers, right? So both of these help us understand skew. You should be able to look at a box plot and see if it tells you anything about skew. Now remember, our box plot is telling us about the median. And so right here, that bar that's inside our interquartile range, well, that tells us that we see greater dispersion to the right of the median. And that's what we see in the picture to the right in the distribution. Now, everyone agree that the opposite would be true here when we have a negative skew. If we have a negative skew, then the box plot's going to look just the opposite. It'd be like if I flipped it in the other direction, right? So make sure you understand how to look at a box plot and see if there is skewness. Now, you might see a graph that has box plots in the vertical direction. So I just showed you what looks like on the left. All right, going left and right, they're horizontal. But look at the graph on the right and you see a graphical construct. This is data visualization where we're putting our box plots vertically. But again, positive skew would simply be up, right? Negative skew would be pulling it down. So hopefully this doesn't confuse you at all if you were to see output that looks like this. So I just want to throw that out there. Now here's a box plot that was used to visualize commute times for employees in two different locations, Los Angeles and New York City. So we've got our box plots. And I want to know what's going on here. What are these dots? I've got commute times, but these are outside of our whiskers. So what is happening? Well, turns out these are outliers in our data set. Remember, when I gave you the example of the box plots a few minutes ago, the very first thing I said was, okay, I'm assuming no outliers. Well, normally the whiskers are bounded by the min and the max, but that's not true here because of having outliers. An outlier in a box plot is defined as an observation falling outside of 1.5 times the interquartile range. So we need to make sure we have that definition down. An outlier is going to be an observation falling outside of 1.5 times the interquartile range. And Excel can flag these for us. More on that later. Now, if we have outliers, then the idea of the min and the max have to be redefined, right? I mean, think about if you had a huge outlier, your box plot would have this like big whisker on it, right? And that's maybe not a good representation because that's just one observation making the box plot whisker pull really long. So the min and the max have to be redefined. And so a box plot is going to define the min and the max to be plus or minus 1.5 times the interquartile range, right? That's why anything outside of this is an outlier. So the max is going to be Q3, right? Our 75th percentile plus 1.5 of the interquartile range. And our min is going to be Q1 minus 1.5 of the interquartile range. So we're basically saying, look, what is our standard definition for max? What is our standard definition for min in a way that allows us to identify outliers? So if that's a little confusing, don't stress yet. I'm about to show you a picture that I think will help. All right, let's focus on this right here. We've got a box in the middle. Q1 is our 25th percentile. Q3 is our 75th percentile, right? And we've got that box showing our interquartile range. Remember that middle 50%. Now, we're going to define our maximum, so look to the right, as Q3, which is our 75th percentile, plus 1.5 times our interquartile range. And anything that falls outside of it is an outlier. Now look to the left at the minimum. We're going to define our minimum as Q1, which is our 25th percentile, minus 1.5 times our interquartile range. That's going to be how we define our minimum. And anything outside of that is going to be an outlier. So here's an example where this very approach is used to look at wine quality. So let's say you're working in a retail situation and consumers are asked to rate 3 different wines. And for each wine, they have to rate it on a scale from 1 to 7. And let's say that you ask them to repeat it 5 times so they get a mean score for each wine for per each consumer. So you show up, you're given a wine, and you're asked to rate it. You're asked to do it 5 times over. You don't know it's necessarily the same wine. You're rating it on a scale to 1 to 7, and then we're going to take your 5 answers for the same wine and average it together. All right? So that's the experiment basically that we're doing. And now we're going to create a box plot. And you see we've got the results for wine A with respect to people's rating, wine B, and wine C. Now, in Excel, when we go to create a box plot, we have to select whether we want inclusive or exclusive of the median. And the only reason we care about that is that it tells Excel what to do if our number of observations is odd. In other words, we're saying, hey, use the median, don't use the median. It's a simple check of a box in Excel, but we all need to do the same things. So because most videos for instruction generally use inclusive of the median, then we're going to do the same. So as you do anything related to the box plot, then just click that box, inclusive of median. So quickly to summarize, we've looked at some very basic data visualization constructs. We agree there are lots of others, and this is not intended to be a class on data visualization, but rather to introduce some basic examples. As you look at these, keep in mind good graphing skills. So we've talked about labeled axes, having legends if they're needed, appropriate titles, citing the data, of course, only if that's relevant. We've talked about not misrepresenting data in any way, that we want to be accurate and not misleading. We've talked about what I call not orphaning the graphs. So don't orphan the graphs in your writing. That means you need to incorporate those graphs. If you write something up for me and I'm reading along and I just find a graph and you've not mentioned it, you've not walked me through the takeaways, then you've orphaned the graphs, and that's not good technical writing, and that is going to detract from your grade. So I'm going to say this multiple times: do not orphan your graphs. Of course, you need to be explaining correctly, which means you're making accurate conclusions, right? And we're going to add on to this as we cover future content. So for now, gang, let me know if you have any questions. Thanks for listening, and I want you to have a fantastic day.